Alright, today we're doing GANs. Darcy and I will be presenting today. Take it away.
Hey, hello everyone. We're doing generative models today. So just to recap, so far we've covered feed-forward neural networks, which is just the simple nodes connected to each other. We've done a few methods on how to train neural networks, and we've gone over convolutional neural networks for images. So today what we're going to be doing is we're going to go over generative and discriminative models, autoencoders at a pretty high level, generative adversarial models, which we call GANs, and then how to train a GAN. So generative versus discriminative models. So a discriminative model is a model that learns the decision boundary to discriminate the data. So basically, it looks at a whole bunch of data and then decides for each data, is this one class or the other? So if we say P is a probability function, we can say Y is the class label and X is the data. So P, given X, given the data, it tries to predict what class is this, and it tries to predict where the decision boundary is. Now, in contrast to that, a generative model, this model learns the probability distribution of the data in order to generate samples from the data. So this is a different probability function. So this is, given a class label, Y, we want to predict the likelihood of some example being from this class. So X isn't in the space of a class label anymore. X is your actual data. So any questions so far? Okay. So this is just another comparison. So on the discriminative on the left, we're predicting a class boundary between the blue circles and the red circles. So that's predicting class based on the data point, blue or red, or predicting blue or red based on where it is in this case. And then on the generative case on the right, it's saying, okay, given that we have this distribution of blue over here and this distribution of red over here, we are going to predict some points that might fall into either one or the other of those distributions. So, like say we want to predict a point that's of the red class, we would put it somewhere in that red oval. And if we want a point of the blue class, we would want it somewhere in that blue oval. So instead of predicting, it's actually generating new points. So autoencoders. So the intuition behind an autoencoder is that it introduces a bottleneck that compresses the input into a latent space representation. So if you see in this network, the two middle bright blue dots, that would be the bottleneck. So see how it gets skinnier and then it gets larger? Right in that middle, that is the bottleneck. And so that is the latent space representation. So the encoder, which is the blue on the left, it turns the input into the latent space. So if we start with our input, we push it through all of those dull blue nodes, and it gets smaller, and then eventually it's represented in those two encoder nodes. And then the decoder reconstructs the input from the latent space representation. So the decoder is the pink nodes on the right, and so it takes whatever's in those bright blue two nodes in the middle, which is the latent space representation, and pushes it through the decoder, and the decoder outputs the decoded output. Any questions? Yes?
So is this just for like compression or stuff?
So this sort of becomes useful. So we'll go over a few cases. I think that's in a later slide. So this is another depiction of the autoencoder latent space. So you have your input, you push it through the purple nodes, and so that's the encoder. And then you get some kind of representation in these three orange nodes in the middle. And so this input has now been compressed into some three-dimensional, in this case, vector. And we say that this is sort of an encoding of our original input. And then the blue nodes on the right, they decode it back into the output. So in the middle part, it's encoded in this special way that this autoencoder encodes it. So a few applications of autoencoders. They can be used for anomaly detection, image reconstruction, denoising, and dimensionality reduction. So like in the case of image reconstruction, you could be given some kind of noisy image and put it through the autoencoder that forces it to focus on the just few important parts in the representation in that middle vector, and then when it decodes it, you'll get out a decent image. Dimensionality reduction is if you have an autoencoder where you try to force the input to be the same as the output, what this autoencoder will try to do is represent your input in fewer nodes in that middle vector right there. So if you have a 6-dimensional input and you force it through this network, you're going to get a 6-dimensional output. And if you want that output to be the same as the input, you have to figure out how to represent it in those 3 nodes in the middle. So you have to contain all of the data of these 6 nodes in 3 nodes instead. So it's dimensionality reduction from 6 to 3. So that makes sense? Yes. Yay. Okay. So autoencoders for image generation. These are not real people. So these images were generated by a GAN using images. Okay. So now into more details. So sort of the intuition of what a generative adversarial network is it has a few different parts. So one part is called D. We can think of it as the detective. It's also called the discriminator. And basically what it does is it looks at real data and fake data, and it tries to figure out what's the real data and what's the fake data. And then we have G, which is the generator, and you can think of it like a forger. So the forger tries to create fake data that the detective thinks is real data. So maybe our generator is an art forger, and so it's trying to recreate the Mona Lisa to look like the actual Mona Lisa so that the detective doesn't know which is which. And the detective is always trying to foil the generator is always trying to foil the detective. And so this is kind of a competition. And how the generator does its generating is it takes some input, some random noisy input, and basically turns itself into a function that maps some kind of noisy input into data that looks like real data, but is generated. So, competition between detective and forger. So, a bit of, yeah.
So, going back to the previous slide, so for it to decide between if data is real or fake, do you have to label that beforehand, or is it just kind of like it learns on its own?
Yeah, so you have to have several real examples, and those you need to know that those are real, and then the generator will provide the fake examples. So like in the beginning, the fake examples won't be very good because the generator is just sort of random upon initialization, but then as this game plays out, it gets better and better, and the discriminator gets better and better. Okay. So, sort of the history of GANs. So in 2014 was the original GAN paper, and that described the most basic case of just you have this discriminator and this generator, and they're battling each other. In 2015, we have DCGAN, which is a deep convolutional GAN, and so it basically is again using convolutional neural networks, so it could be applied to images. In 2016, there was the InfoGAN, so it learned disentangled representations, so basically it learned how to do vector arithmetic in its generation space. We're not going to go too deep into that. And then 2017 was CycleGAN, and that does image-to-image translation. So given an image, you output an image as well. And there are many more. So this is image-to-image translation. So for example, in this case, we're transforming a work done by Monet into a photo. In this one, we're transforming some zebras into horses, a picture of a mountain in the summer to the mountain in the winter, and so on. So this is CycleGAN. And then we have some more fake faces. These were all generated by a GAN, and none of these people exist. Oh, you want, okay. Okay, so every time you reload this website, it gives you a new generated image of a fake person. So as the title of the website says, this person does not exist. And neither does this one. Yeah, so you can all play with this afterwards. Yeah. Okay. And this is an example of style transfer. So given this image, which is an actual image, what the GAN does is it takes in the image and then it transferred this style into the style of this painting. I don't know who did that. But you see the content of the image is the same, like it's a row of houses and this spire up here. But the style is the style of this painting down here. And same with these two as well. So how do GANs actually work? So we have two opposing models, right? On one side we have the forger, which is the generator. And the generator generates fake examples. And then on the other side, we have the detective, which is the discriminator. And the discriminator tries to figure out, is this example a real example or did it come from the generator? So first we're going to have some definitions. So we define X as the space in which the samples reside. So it's the space that the generator outputs to and the discriminator discriminates in. So for example, X could be the space of RGB images. So the generator would be generating RGB images, pictures, and then the discriminator would be looking at different pictures and trying to figure out, did this come from the generator or is this real? Now Z is just some space. So it's the space that goes into the generator so that the generator can generate some example. So like the generator can't just make something from nothing, right? It needs to have some input. So Z is basically noise, and then it goes through the generator, which is, you can think of it as a function, and it maps Z into some place in X. So Z might just be some random vector. So G will take in this random vector, and then G from that will output some kind of image in X. So you understand the difference between X and Z. So Z is just some random space, X is the space, X is the interesting space. So then we have PG, and that's the distribution in X of the outputs of the generator. So if the generator like outputs a whole bunch of images, PG is the distribution of where all of those outputs landed in X. So like if G just outputs a bunch of blue images, then PG is around the blue area of the image space. Now P data is the distribution in X of the actual data. So if all of the real images are green, because they're outside, P data will be around the green part of the space of X, which in this example is images, yeah?
Just to make sure X is what the generator is actually creating, and Z is the input into the generator, or input into the discriminator, which is an actual image that, right?
So the input into the discriminator is X. So X is, yeah. So Z is just some random noise that the generator uses to make an example in X. The discriminator looks at examples in X. Okay, great. So we have the generator. So as I've been saying, given a random input from Z, it outputs an example in X. And G outputs examples in the distribution PG in X. Okay? And so remember, GZ is our art forger. And then the discriminator, given an example in X, output a probability that it is a real example. So remember, X is like the image space. So D outputs the probability that the examples came from P data, which is the distribution of the real examples, rather than PG, which is the distribution of the generated examples. Remember, G outputs into PG. P data is the actual real data's distribution. And so D outputs a probability between 0 and 1 that the example is from the data and not from the generator. All good? Okay, so again, definition. So the goal of the generator is to map Z, the random input, into a distribution PG and X, which is, for example, our image space. And we want PG to converge to P data. So what this means is we want the outputs of the generator to converge very closely to the actual examples. We want these distributions to be very close. Now, the goal of the discriminator is always to determine whether an example in X comes from P data or PG. So the discriminator is always trying to figure out, is this example real or does this example come from the generator? And the accuracy of the generator is 1/2 when PG has converged to P data. So when the generator is outputting examples that are indistinguishable from real data, then D is basically guessing whether this example is real or fake. And so its accuracy is 1/2, because it's probability. So to motivate this game we're sort of playing between the generator and discriminator, we define this value function. And we will parse through this in the next few slides. So the generator's goal is to create convincing generated examples. And given this value function on the previous slide, that value function is small when the discriminator predicts that the generated example is from the data. So when the discriminator thinks that the generated example is from the data, that basically means the generator has fooled the discriminator. The discriminator wants to realize that this generated example is generated, but the generator has fooled the discriminator because the discriminator thinks that it came from real data. So G wants to minimize the value function. And this is one term from the value function. And as we can see, this just means expectation. This Z just means we're only concerned with inputs that are from Z, which is the noisy space, just the random noise that the generator gets. And so we have log of 1 minus D of G of Z. So G of Z, that's our fake example. Now D of G of Z is the probability that the discriminator has predicted that this example comes from the real data. So this is small when D of G of Z is close to 1, and D of G of Z is close to 1 when the discriminator thinks that the generated example is from the data. Has everyone got that, or do you want a minute to think? Because that was a lot to take in. All good? We'll take your silence as a yes. Okay, so the discriminator's goal is always to correctly distinguish between real and generated examples. So for the discriminator, the value function, which remember we defined a few slides ago, is large when D predicts that examples from data are from the data and examples from the generator are from the generator. So for the discriminator, the value function is large when the discriminator is correct. So the discriminator wants to maximize the value function. So these are two terms from the value function that concern the discriminator. So this term over here, this is expectation. This means we're concerned with all of the examples that come from the real distribution. So this is overall real examples. And this term, log of D of x, this is large when D of x is close to 1, and that is when the discriminator identifies the real examples as real. So in this part of the function, we're only giving D the real examples. And so for all the real examples, we want D to output 1, because 1 means that it's from the actual data. And now, this term over here, we have the expectation, and this is over Z, which is the random noisy space that the generator samples from. So now, 1 minus D of G of Z is large when D of G of Z is close to 0. So that's when the discriminator identifies the generated example as generated. So G of Z outputs some example in X, right? So D of some fake example, that's going to be close to 0 if the discriminator correctly identifies it as fake. So the discriminator sees this fake example and outputs a probability close to 0, and that's when it correctly identifies that this is a generated example. So D wants to maximize this whole function. So does everyone understand those two terms? Yes? Okay, I got a few nods. So the GAN definition is this two-player minimax game. D is trying to correctly classify the examples. G is trying to fool D. So G tries to minimize and D tries to maximize our value function from before. So this is just everything we've seen. So this notation means that we want to choose G to minimize this value function. We want to choose D to maximize this value function. And then this term over here, this is large when D is correct, and this is small when G fools D. So G wants this to be small, D wants this to be large, and these two different models are always competing. So eventually, we want our model to converge to something useful, right? So this is an image from the original GAN paper that says it pretty nicely. So these black dots right here, this is P data, so that's the distribution in X of the actual data. Now this green curve over here is the distribution of the generated examples. And this blue wiggly line, that's D's prediction from given each X, how likely is it that it's from the real data rather than the generated data. So we see initially, in this first step, G is taking in some Z, mapping it to an X, but this distribution that it's mapping out to, it's not really close to the real data. So the discriminator is able to pretty accurately predict that, oh, examples from over here, they're probably real, so this wiggle is high over here, but these examples over here, they're probably fake, so this wiggle is lower down over here. And then as we go on through training, G gets better and better at producing examples that look real but are still generated. And so eventually we converge, where PG is indistinguishable from P data. And at this point, the discriminator has no idea whether any example in X came from the discriminator or came from the generator or if it's real. And this is the goal, right? So at this point, D predicts 1/2, and then we have a generator that basically takes in some random noise and generates some example that looks exactly like your images that you started out with. So now we have this function, the generator, and we can use it to just generate images, like we saw with those fake faces. So, on to Devin.
Okay, so real quick before I get started, just one quick announcement. There's an MIC cross-community lunch this weekend, so it's like MIC, there's BU MIC, there's Harvard MIC, and there's MIT MIC. So there's like this cross-community event this weekend. There's a Facebook event. We'll post it onto Piazza if you want to join. So it's like people just come together, have some food. So like Saturday, around noonish, I believe, maybe 1, something like that. So if you're interested in meeting other people from like Harvard, MIT, or like even still within BU, who are all interested in machine learning, doing cool things, this will be a great event to do that. So we'll put a link for that onto Piazza. Make sure to mark that you're going if you want to go, so that Justin, who's organizing this event, will be able to like update the reservation so the restaurant knows how many people to expect. So yes, do that if you'd like. Now, after that brief intermission, going to training GANs. So this will kind of be a recap of what Darcy went over, while also kind of looking for more of an algorithmic perspective, like, okay, what are the actual steps you will take in order to train a GAN? Like, hey, we talked about sampling, or like we're generating from random space, how do we kind of do that, things like that. And then we have code, which we'll be going into implementing a GAN for generating MNIST data, handwritten digit data, using GAN, so that's kind of cool. So this is the figure from the paper. This is the full algorithm. We'll literally be going through this like line by line, basically. So just a quick overview. It's kind of like we're going over the full data set for like some number of epochs. We're going to be updating the discriminator, and then we're going to be updating the generator. So this is directly taken from the paper. You see how we're sampling different noise samples. We're going to sample different data samples, and we're going to use those different samples to update our discriminator. And then we'll take more samples, and then we'll use that to update our generator. So going into it, the very first step coming literally straight from here. Sample a mini batch of M noise samples, which will then give you this vector of vectors. And these are going to be random. So this is going to come from a random distribution. I believe in my code I sample from just your standard normal distribution. There's actually some interesting research on, okay, what are the best distributions to sample from, but it works just fine if you're sampling from the normal distribution. So you just end up with this vector of some arbitrary length, generally much smaller than the vector you'd have if you enrolled the full image. And then you're going to take those samples that you made and you're going to run it through the generator. So what that's doing right there is it's going to get these like fake examples. So if this was for generating images, you would get fake images after this because you just took these noise vectors and ran it through the generator. So that's what we're doing. We're taking these noise vectors, we're going to run it through the generator, and then we're going to end up with a whole mini batch of fake examples. Now the next thing we're going to do is we're going to sample a mini batch of, again, M examples from the true data set. So now we have our fake examples and our real examples. Now with these real and fake examples, we're going to update the discriminator. We update the discriminator before we update the generator. So we get the probability scores. We're just going to run in these real and these fake examples through, and we'll get two sets of probability scores that we'll know come from either the real or fake distribution. So if the discriminator was doing well, the probability scores for coming from those real examples should be much higher than those in the fake probability scores. So now, after we do this step, we're going to end up with like two lists of vectors of probability scores corresponding to our real and our fake rake. So now, next step, we're going to use these probability scores to update the discriminator's parameters. So we went back to that like min-max game with those expected values. Now we're going to kind of be distilling this into a loss function, which looks pretty much exactly like those equations. Now, breaking this down farther, we just made these probability scores, and so where this actually factors in is you have those real probability scores as being that d of x, so the probability that those real examples are being classified as real by the discriminator, and for the fake examples as well. That extra step of running through the generator was to get that nested g of z right there. So now we have this equation that, as Darcy explained, is going to have this min-max effect when we update the generator. Ooh, that should be d instead of g. I'm sorry on those parameters. So we're updating the discriminator. We're going to update those weights. So this loss function is going to push it to hopefully next time around make the discriminator do a better job. Now we've updated the discriminator. We made our gradient descent step, gradient learning rate. We're all good there. Now we're going to sample a mini batch of M noise examples. Again, totally different new examples, not the same ones we just did before. And then we're going to run the samples again through the generator. And again, we're going to end up with some fake examples. So very similar to what we did in the first step. This time around, we have a new sample though. Now we get probability scores from the new fake examples. And so again, just end up a list of all these probability scores. Now, we again do this update, but now for the generator. So that d of g of z right there is those fake probability scores that we just calculated. And now we plug it into this equation, and we make our gradient descent as well. Yes. Okay, so this is full recap here. We go through, we update the discriminator, and then we go through and update the generator. And each time of those, we're going to have to sample noise from some distribution. We're going to have to run it through a generator, and then we're going to have to run those fake examples through the discriminator, and we'll use those to make these updates. Are there any questions on this?
How do you gauge how well the game is actually working? Because you have basically two connections.
Yes, exactly. So you should literally see a difference in the losses for, here, I will literally show you this. So going down here, where we're going, it's like right here you see the discriminator loss. It's much lower than the generator loss. So like in this particular time in training, the discriminator is doing better than the generator. Now you see an update again, and then the discriminator wins as well. And so you'll continue to see this trend. But what's happening in between those two steps, like after we update the discriminator, that should be doing better than the generator then. So it's like we make the discriminator better, and then by making the discriminator better, we'll be able to make the generator better. And you see how that's kind of like a feedback loop that's going to always like improve both models and hopefully have that generator converge to like that real data. Yeah, you would be able to do a plot if you like took a loss value like after this discriminator and compared it to the generator. Um, but I didn't do that.
I mean, you can also say that
Um,
the discriminators would go
okay, yeah, it's like always two perspectives here. How you can do it. Yeah. So this is like the algorithm's perspective on how to do this. It's kind of mostly focused on these samplings and then how you use those samples to make these updates. Then talking about some issues here when you're training GANs are really, really tricky to train. Like doing this code here, if you change like little things like the number of like hidden units in like your neural network, that could totally mess it up. Like it needs to be like balanced with the generator and the discriminator. If you have like different learning rates, that will mess it up as well. So it's like it's kind of tricky to go around and actually get this right. So it's a lot of hyperparameter tuning. So some like very like defined problems is this idea of non-convergence. So you may end up where it's like no one's really winning this min-max game. So it's like the generator is never getting to a point where it's actually outputting something that's like semantically meaningful. It's just kind of outputting noise because maybe the discriminator found to some local minima that isn't what we want. So you always have to like watch it through training, and if it does, you might have to just restart it again. Maybe make some updates to hyperparameters. Mode collapse is another problem. So this image on the right is an example of mode collapse. You see that it's only outputting ones. And while that's totally valid and it could totally be like fooling the discriminator, it's not what we want as well. You want to have these outputs across all these classes you have, so you want to see all these digits. So again, back to this example, you see that where it's properly working, you're getting outputs like something like a 7, a 1, 4, maybe a 5 here, like 9, 4. So you want to see like output across all the classes that are available in that actual data. And then just diminished gradient. So that comes through the fact of one of these equations that we use here. Okay, I forget which one. Ask me after if you want to go into that. But so the way around that is actually don't use these actual equations that are found in the paper. You end up using like binary cross entropy is what I use in this example here, and assign like zeros as being fake, 1 as being real. So actually using data like labels instead of just those probability scores. Then again, like I was saying, it's very sensitive to hyperparameters. So it's like doing GAN stuff requires a lot of fine tuning, a lot of patience sitting there, trying to work through it, trying different combinations. Yes. Any questions on these issues? Mode collapse. Injecting noise into the training. So when you do the discriminator, the part where right before you feed into this discriminator right here, so it's like for both X and the fake examples, you also inject like a random thing of noise as well, just like scaled by some epsilon value. So it's like the image that you're adding noise to, you just make it noisier. So then it's not really like locking onto specific properties. And I think there is a mathematical proof that goes into why adding noise, like you will see better results. So there's like all these little tricks around training GANs. It would be worthwhile if you're interested in doing a GAN project to go through and read all these things about GANs, how to train them better. This one blog post does a pretty good job of like introducing these problems, how to get around it. If you want to do a GAN project, let us know, and then we'll point you in the right directions here. Yeah. Any more questions? You end up with some nice images, pretty much. That's defined by the problem you're trying to solve, really. So in the case, we saw a lot of people like trying to do like images for like different faces, different people. So really just, you want something that will be able to generate these new data points, essentially. That's what you're getting out of GANs. But you also saw in some of these applications like style transfer. you're able to kind of get this idea of style out of it, um, and then apply that onto a new image. So it's like being able to extract like these ideas that are hard to just code in. GANs are like a good way to do it, like because like how the hell would you like write a program to extract the style of like a painting? Like that's so abstract. I think this is one of like the coolest properties of machine learning. They're able to like get something that's so abstract like style and be able to get like a quantitative metric for that and then apply that onto a new image and actually get something that works. Yeah. And then kind of going into that some more. So we mentioned beforehand this paper InfoGAN. We talked about like a little bit like vector arithmetic. So what's like actually happening here is in these generated images, you may end up with things. So it's like all these are generated images from GAN. So there was like some latent vector. There's these vectors that you can see being sent into this generator, and you're getting these outputs. And some of them you may end up with sunglasses on people, and some of them you may end up with not. So like, what's the difference between that? Well, you can literally take those like latent vectors, those random vectors, and then average out the ones that produce just people's faces, and then you get people's faces with sunglasses, and then you get the average person as well, like sunglasses, no sunglasses, and then the difference between those averages is kind of like this latent idea, this abstract idea of a person like adding sunglasses onto a person. So then if you take this difference, which will be that like idea, abstract idea of sunglasses, and add that to a person without sunglasses, you will literally end up with an image of people with sunglasses. So it's this really cool way of like abstracting out these like notions and these specific parts, and then being able to apply that farther onto newly generated images. So that's like a really, really cool property of GANs. If you're familiar with like Word2Vec, which is a language modeling thing for NLP, it also has a very similar property of this vector arithmetic. So if you think this is cool, recommend also checking Word2Vec. Might do a paper discussion on that sometime if people are interested. But yeah, so that's the thing we have for GANs, all this training, this idea of min-max game, how we generate these images. Are there any questions here before we move on to project ideas?
Can I go back to this last, those GAN projects?
GAN projects, which one?
So, actual
Payment, yes.
what is it
The one that the type of GAN that is able to do this.
called?
Cycle GAN, yeah.
Cyclic.
Yes, literally, it is this one here, cycle GAN. So it's like cycled because there's like two GANs that are like playing with each other and like a cycle. That's what that name comes. So it's like translating images. So it's like zebra to horses is a form of like style transfer, because like there's a style of zebras versus a style of horses. Same with like winter, summer, Monet. Yeah. That'd be a really cool project if someone wants to do it, like style transfer. That'd be fun. Any more questions? Yeah. So going into more project idea stuff. So this came from like one blog post on DistillPub, which is a really, really nice like blog. I feel bad calling it a blog because it's like so much more in depth, so much more comprehensive than like a Medium post. Like they talk about all these different like research questions specifically around GANs. So if you're feeling pretty ambitious, maybe doing something like simple around these ideas, these problems, can be a really cool project. So feel free to find this linked in the slides. I believe the slides are. Nope. I'll add this link to the problem document, the product document rather. So the first one is talking about trade-offs between GANs and other generative models. There's been some debate recently on if GANs or autoencoders are better for certain things. Paper came out, DeepMind, they were saying like, oh, autoencoders are doing just as well, if not better. So kind of a competition there between autoencoders and GANs. Yes. Like, there's no concept of adversarial. Like, this min-maxing, nothing about that in autoencoders. Just, can we match this input to this out? Can we match this input, compress it down to some latent representation, and then build it back up and get the same input. Get the same, have our output be the same as the input. So there is a coding example on this using PyTorch. This is a pure PyTorch tutorial. But real quick, let's go through this code, just point out like the big parts that we talked about. So this top two cells, pretty standard stuff we have seen when like working with PyTorch. I always like to keep a cell that deals with hyperparameters. So if you want to go around and play with these metrics, feel free. You can see how it's going to affect the training. Then we have two networks here. This is a more concise way of defining neural networks in PyTorch using this sequential method. That you just stack the different layers followed by different activation functions you want to use. And so for the discriminator, you see we're using the sigmoid activation as our output, so we get that probability score, just a value between 0 and 1. And then for our generator, we have tanh, which is between -1 and 1, so we're going to be able to have like a full varying scale for our output images. And then PyTorch way to load data, just use data sets coming from this module, Torch Vision. Just easy access to the MS data set, which is all these handwritten digits. Then we're turning into a tensor so that machine learning can apply like neural networks to it, how it actually be arrays, not some weird image format through Python. We normalize it so that it's going to speed up our gradient descent training. And then load into a data loader, just a Pythonic or a PyTorch way of loading in our data, handling batch size, shuffling, just some more advanced stuff to just keep it speeding through our GPU. Then little image here just so we can see, maybe we can use that. I'm just gonna delete that, never mind. So now we're gonna take our discriminator, our generator, and we're going to push them onto our devices. And then we are also going to have different optimizers, note, for the discriminator and the generator, because the optimizer is what you use to make that step, like you'll literally see optim.step, and that's that update to these parameters. So we only want to be updating the discriminator at one time, and then the generator at another time. And then our loss function, also known as the criterion in this case, we're using what's called binary cross-entropy loss because there's either two outputs here, it's either real or it's fake. So that's that binary, 0 being fake, 1 being it's real. And now comes the training loop, which is like the full meat of this like Minimax game happening. So one thing we didn't really talk about beforehand is that we actually have labels now. So these labels are just going to be zeros or ones, corresponding to this binary cross entropy. Fake are just going to be zeros. Real images are going to be ones, and they're going to be the same size as that like sample M mini batch in a mini batch. Then we're going to run it through to update the discriminator section. We're going to get the logics, which is going to be actually let me change that. Logic might not be the right word here, but we're going to get these probability scores for the discriminator. Based on real images, and we're going to get the probability scores from the discriminator based on these fake images. And now we're going to get different loss values based on if it was real or if it was fake. And the total loss for the discriminator is going to be how does it handle classifying real data and how does it handle classifying fake data. And then we're going to make the update just to the discriminator at this point. Zero grad, again, just the PyTorch way to get rid of all the gradients that were accumulated over time when calling dot backward. So when we call dot backward, it's only on the gradients that we just calculated. Yeah, so backpropagate, and then we step. So we're updating the discriminator. The discriminator should be better now and should do a better job of classifying real versus fake. Now we have a whole update generator section. We're going to get some more random noise, and this rand_n function is sampling from a normal distribution. Just PyTorch gives us a really easy way to get at a specific size. And then we get the fake images by running through the generator, and then we get the fake probability scores from running it through the discriminator. And the generator only cares about how the discriminator is going to do on the images that it just generated. So we just have one loss calculation here, and then we go ahead and we update. And now just keep track of this so that we can see how we're doing throughout time here. And then we just print out different epoch information, and then just a little right here so we can see the images that are actually being created by this generator. So let's run this. Any questions about this code here? Feel free to ping on Piazza if you want to go through this deeper. If you have any questions, then if you want to use Piazza as a resource, start asking questions, things if you want to go through things, especially as we get closer to projects. I think that would be a really good resource for all of you. So as you can see, we're going through an epoch, and then we get an error, and that's why we needed that motherfucker. Okay, here we go. Don't randomly delete things. It's a bad idea. Any questions? Anything? Life? Midterms coming up? So you see at the beginning, it's kind of noisy still, not really outputting any distinct digits. It's still kind of figuring out what it is. But it has figured out that most of the white pixels are going to be very much clustered in the center. And it is kind of getting some maybe specific lines, some loops, some curves. So it has already learned a good amount already. Now we get farther here. It's really liking the loops right now, but you can see maybe something like a 5 is coming through. Yeah. So it's really fun to just keep us watching. A lot of times it does need to train for longer. I originally had this train for something 200 epochs. And you just see much better results when you go that length, and you can really fine tune that generator. So just let this run, keep going through it, play with the hyperparameters, see how that's going to affect these images at the end here. Let's try something. I'll show you how finicky this is. Type of parameters. So if I change so if we make this if we have different hidden sizes, so the number of nodes in these hidden layers. So if we have one for the generator and we have one for the discriminator, if we make this much bigger, twice as big, size 12. So discriminator here, 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 here. Transfer. And I believe this should mess everything up. Not too bad, right? But you can see it's learning it's in the center, but it wasn't learning as many different curves and stuff as we saw last time. Kind of just have to watch it over time. Like there's no, this is still like kind of considered unsupervised learning because you don't really need to know, you don't need to spend time like labeling any images. You know whether or not it's going to be real or fake because you just generated the fake ones, so you just need a massive field data. So there's no like explicit loss that you have here to know whether or not it's good or bad. Okay, this seems to actually be okay. Data set. I would recommend like a more advanced GAN architecture, maybe something like conditional GAN. So in the generator, how before we were just sending in that like latent vector, just some random noise. You could also append to it like a class label. So you know now it requires like more understanding of your data, but for like digits that'd be really easy. You could append like a 0, 1, 3, like 9, whatever. So then it would learn to take that, and you'd have an additional loss there. So it's that output might be the same class as that additional appending to that random noise. So then it's going to help it like focus on like discriminating between multiple classes and not just falling into like mode collapse. Also, injecting random noise again is a very good trick. This one does seem to be falling for mode collapse with just ones right now. So yeah, you end up with things like that happening. We just changed like a pretty, not too minor of a hyperparameter, but still the generator probably is saying, okay, to keep up with the discriminator now, because the discriminator has like so many more parameters now to like figure out what to like say is real or fake. It decided, okay, we got really good right away at generating ones. Let's just do that, and it seems to be what it's doing. So yeah, you can see like all these problems that just arise with some pretty simple change. So yeah. Okay. Also, going more into projects. So we have this document. If you haven't seen this before, it's linked on week 6 and week 7 resources on Piazza. So I think next week for sure, we're literally going to be sitting down and like kind of figuring out what your project will be, like kind of write a paragraph of what you want your project to be, and then start doing a game plan, talking with everyone on how you want to approach this problem. So there's a lot of good links here. If you're unsure, if you have no indication of what you want to do, I'd recommend finding a Kaggle competition and then working towards that. Otherwise, there's a lot of good links here. Check them out. Add a comment to something you're interested in if you want to find a teammate or a couple others to work on that project with. Besides that, I think that's it. Yes. Julius, do we have? Okay, there will be. Keep an eye out for it. Might be less because the construction is kind of messing things up a bit. But yeah, try to fill that out. Yeah. That should be it.